This video introduces the idea of an abundance diagram, where we look at percent abundance of aqueous species versus pH. And we'll begin by reviewing information from Chem 105, our first semester course. In that course, you had to list the formulas for the 6 strong acids and their conjugate bases in alphabetical order by symbol. So please pause the video and write those onto the accompanying handout. Okay, I hope you were able to get hydrobromic acid, hydrochloric acid, perchloric acid, hydrogen iodide, nitric acid, and sulfuric acid, and their conjugate bases, in each case missing an H+, Br-, Cl-, ClO4-, I-, NO3-. The first conjugate base for sulfuric acid is hydrogen sulfate ion, and if you take off yet another hydrogen, you get sulfate ion. You should also be able to review the strong bases, the group 1 and 2 cations accompanying OH-. So for instance, sodium hydroxide or barium hydroxide are both strong bases. Another piece of outcome 10 from last semester was to be able to identify compounds as strong acid, strong base, neutral salt, or molecule. In this course, Chem 2200, we'll actually add weak acid, weak base, weakly acidic salt, and weakly basic salt because you learned all of those last semester. So I'd like you to pause the video here and identify each of these species. For instance, we'll do sodium hydroxide together. Sodium hydroxide is a strong base, so you would mark an X in this box. Please pause the video and fill in your chart. All right, let's see how you did. We agreed that sodium hydroxide was a strong base. This C5H5N is actually pyridine, and that's one of the weak bases you should recognize. Oh, that's a much better check mark this time. Calcium chloride has calcium 2+, which is the cation that comes with a strong base, and Cl-, which is the anion that comes with a strong acid. So this is a neutral salt. The cation is too weak to act as an acid, and the anion is too weak to act as a weak base. So a neutral salt. This I hope everyone recognizes as acetic acid, a weak acid. Now you know it as a carboxylic acid. Potassium fluoride is a salt, but when you split it apart, K+ is one of the alkali metal cations, so it doesn't act as an acid. F-, however, is the conjugate base of HF, which is a weak acid. So this, being the conjugate base of a weak acid, would be a weak base, F-. That makes this a weakly basic salt. Perchloric acid is one of the ones you had to memorize. It's a strong acid. CH3NH3 bromide. So this is methyl ammonium bromide, and that should make more sense now that we've looked at some functional groups. Bromide is the conjugate base of a strong acid, and therefore it's such a weak base that it doesn't act as a base. It's a neutral anion. Yes, a neutral anion in aqueous solution. But the CH3NH3+, the methyl ammonium ion, is the conjugate acid of a weak base, methylamine. So this is a weakly acidic salt. It's got a weak acid, the conjugate acid of a weak base, as its cation. Lithium hydroxide should be easy to recognize as a strong base. And ethanol, an alcohol, is now much easier than it was last semester, I think, to recognize as a straight-up molecule with no acid or base properties. The next outcome we'll go over is outcome 11. And in this case, you could be given a strong acid as a recipe, a strong base as a recipe, a neutral salt as a recipe, or a molecule, and you would then be asked to write appropriate chemical equations for any reactions that occur, complete with state symbols. Where appropriate, identify conjugate acid and base pairs in the reaction equations, and you have to know when it's appropriate to do that. Create a molecular representation showing at least 10 water molecules, and assume that you start with 6 recipe molecules, so 6 HCl molecules, what is actually floating around in the solution. And finally, give a legend that shows the formula represented by each symbol and lists how many of that symbol are in the picture. So I'd like you to pause, probably take out a new sheet of paper, but you can use your accompanying guide and fill in this information for hydrochloric acid. All right, hopefully that was straightforward. There is probably a need to review some of this. You should practice one of each type of molecule before moving on to the next section, but we'll look at the answers for HCl first. The one reaction that occurs is hydrochloric acid, as an acid, reacts with water and donates an H plus to the water to make H3O plus. That leaves Cl minus as an anion all by itself in the solution. This occurs with a single arrow, which means that every bit of the HCl reacts with the water. There's so much water around that not every water will react, but every HCl that you put in the water will react and will make H3O plus and Cl minus. Then we also have the water-water reaction, which occurs whenever you have water present. Water reacts with itself, and with a double arrow reaction indicating that this does not go all the way. In fact, rule of thumb is like 1 in 10 million molecules might typically do this, though the exact number is governed by the Ka, or the acidity constant. In this case, it would be the Kw, the water constant. Sorry, from this water donates an H plus to this water, and this water becomes OH minus, this water becomes H3O plus. And we've labeled the conjugate acid, conjugate base pairs, conjugate acid, conjugate base. This is also a conjugate base, conjugate acid pair. In every case, the acid has one more H plus than its conjugate base. It's a little confusing in the water reaction, but you can review the videos from last semester. Now we're going to look at an if table, initial, change, final. That's where the if comes from. So initial, final. If we start with 6 molecules of HCl and lots of water as the solvent, no H3O plus or Cl minus present, what happens because of this single arrow is that all 6 of those HCl's will react. They will have to react with 6 waters, so we'll lose 6 waters. Will form 6 H3O pluses and 6 Cl minuses. And the change line is always in the same ratio as the stoichiometric coefficients in the reaction, which in this case are just 1. If we start with 6 and lose 6, we end up with no HCl's. If we start with lots and lose 6, we still have lots at the end. If we add 6, we now have 6, and if we add 6 to nothing, we have 6 Cl minuses present. Similarly, with the water-water reaction, there's going to be one difference because of the double arrow here. We have an ice table instead of an if table. Initial, change, equilibrium. If we start with lots, only a little tiny bit reacts. We can't show 1 out of 10 million very easily in pictures, so we made the convention that we say 1 reacts. So we have lots of water. 1 water reacts with 1 water, makes 1 H3O plus and 1 OH minus. So at equilibrium, we still have lots of water, but 1 H3O plus and 1 OH minus in our picture. That way overstates the amount of H3O plus and OH minus present from this reaction compared to this reaction. These numbers would really be more like 10 million, and these would be 1. But it lets us look at what we have in solution. HCl, we have no HCl left in the final line. Water, we still have lots, and we'll always represent lots with 10. 6 H3O pluses from this first reaction, that's the 6 here, plus 1 more from the water-water reaction. So we have 7 H3O plus, 6 Cl minuses, and 1 OH minus from the water-water reaction. If we draw a picture of this, I've got everything in this picture except the waters. So you can add 10 X's or something all over the picture to make waters. But you can see I have no HCl's. H3O pluses, I have 1, 2, 3, 4, 5, 6, 7. I have 1 OH minus, and I have 1, 2, 3, 4, 5, 6 Cl minus. And again, there would need to be at least 10 waters. In reality, bazillions of waters in this picture. All right, with all that back in your mind, go ahead and practice a sodium hydroxide recipe, perhaps a calcium chloride recipe, and a methanol recipe, just to remember what these all look like. Those won't be in the video, but you can ask other people about them in class, or you can review the videos from last semester. One more little piece we're going to add is the pH calculation for a strong acid, strong base, neutral salt solution. So if I gave you a strong acid, HCl, and told you the concentration of it, you could write the reaction, and then please pause the video and fill in an if table and calculate the pH of this solution. All right, let's see how you did. Initially, we have 0.03 molar this time, 3 times 10 to the minus 2 molar. Lots of water still, no H3O plus and no Cl minus. Our change, because of the single arrow, is that all of the HCl reacts. The same amount of water must react with it. The same amount of H3O plus will be formed and the same amount of Cl minus because it's 1 to 1 to 1 to 1 stoichiometry. The result for the final solution is that no HCl remains, lots of water, 0.03 molar H3O plus and 0.03 molar Cl minus. The significance of this is that the pH equals minus log of the H3O plus. So since we know the H3O plus, we plug that into this equation and we calculate a pH of 1.52. Now we are finally ready to move on to the new idea for this semester, which is percent abundance diagrams. Here we have percent abundance of some species versus pH. So I would like you to pause the video, think about what pH means. What does it mean for there to be a low pH and what does it mean for there to be a high pH? And figure out what are the two species that are shown on this graph that would be present in every aqueous solution, but water isn't one of them. And which of those is which on these lines? All right, I hope you were able to figure this out. The dashed line is very low abundance, near 0% abundance, until a pH of 7, at which point it becomes the more predominant species and remains so all the way down into the low pH. If you think about what happens at low pH, that's acidic solutions, and that's where H3O plus is much higher than OH minus. So that's how we know that the H3O plus line is the one that rises, crosses with the OH minus line at pH of 7, and comes down and is a minor species after that. Likewise, the OH minus is what is abundant at basic pHs above 7, so it's the high species, 100% abundant nearly, until you get near pH 7. At pH 7, both of them are 50% abundant. We have exactly the same amount of H3O plus and OH minus at a neutral pH, and that's where those lines cross, right at a pH of 7. They're both at 50% there. And then the OH minus goes down and is a very minor species at all acidic pHs. H3O plus far outnumbers OH minus at acidic pHs. This is the base for every future diagram we'll look at because all our solutions will be in water this semester. So now I'd like you to look at your results from that 3 times 10 to the minus 2 molar HCl solution and try to label all 3 lines in this diagram. Go ahead and pause the video and fill in your own sheet, your own handout. All right, how did this one go? I presume you were able to figure out that the H3O plus is still the one that rises at low pH and the OH minus is the one that rises at high pH. So that leaves the question of what this last line is. And if you look at your picture that you drew for HCl solution, the only 3 species that are actually floating around are H3O plus, OH minus, and Cl minus. So it had to be chloride ion. And if you look carefully at the line, it makes perfect sense. Chloride doesn't care what pH it is. It's 100% abundant at all pHs. Which brings us to an interesting question. What pH was this actually present at? What did we calculate for the pH of 3 times 10 to the minus 2 molar HCl? It was pH 1.52. So if we follow up at 1.52, that tells us it's like a snapshot of the solution at a pH of 1.52. This is the region that describes the 3 times 10 to the minus 2 molar HCl solution, specifically right at that pH. But you should be able to circle the general region pretty easily. What are the major and minor species at this pH? Well, chloride is major, H3O plus is major, those 2 lines are both 100% there, and the minor species is OH minus. That's neat. It's a cool thing you can do with this diagram, but you can do something else with this diagram. You can say, what would be the major species at a pH of 2? So let's move over here. Oh, well, that's kind of boring. It's exactly the same. Major are Cl minus and H3O plus, and minor is OH minus. How about a pH of 5? Still the same result. OH minus is minor, but not quite as minor as it was before. H3O plus is major, but not quite as major as it was before, and chloride is still a major species. How about pH 11? Run up to pH 11 and just look at the diagram. At a pH of 11, H3O plus is very, very minor species. It's almost 0% abundant. But OH minus is very abundant, and Cl minus is as well. So we've completely changed, or at least swapped H3O plus and OH minus at a pH of 11 as major and minor species. Again, OH minus and Cl minus are major species. H3O plus, if you follow it down, is a minor species at pH 11. All right, time to review another type of species. Outcome 22 asked you to choose either, you would be given either a weak acid or a weak base recipe, and you'd be asked to still draw the picture and write all the chemical equations. So go ahead and pause the video and fill in the answers for acetic acid as a recipe species for outcome 22. Alrighty, let's look at the answer for this one. You should have written a reaction of the weak acid and water with a double arrow this time, because this is a weak acid, to make H3O plus and CH3COO minus, the acetate anion. Identify your conjugate acid, conjugate base pairs. And again, the water-water reaction will be in all of these. Because this is an equilibrium, we would do initial change equilibrium and ice table for both of them. In the top one, it would be starting with 6 recipe species. We only lose one of those because that's our convention for a double arrow. We lose 1 water, gain an H3O plus and an acetate. So at equilibrium, we have still 5 acetic acid molecules, lots of water, 1 H3O plus and 1 acetate. And the water-water reaction looks the same as always. So what's floating around in solution? Just go through everything in the reactions. Acetic acid, there are still 5 molecules left. Water, we have lots. H3O plus, we have 1 from this reaction and 1 from this reaction for a total of 2. Acetate anion, 1 from this reaction, and OH minus, 1 from this reaction at the end. What does that look like? Okay, this is a slightly lame picture, but if you take the gray blob as CH3CO, and then there's an O and an H, this is acetic acid, a strange representation, but acetic acid. So we have 5 acetic acids, 1, 2, 3, 4, 5, 2 H3O pluses, 1 OH minus, and this thing is an acetate anion, CH3COO minus. All right, now let's calculate the pH of that solution. Not quite as trivial as a strong acid or strong base. Remember that you actually have to write a complete ice table, show your assumptions, use a Ka. So here's the initial change, final, and this time we start with 1.5 molar, lots, none, none. Our change is x. That's what we're trying to solve for. We don't know how far this is going to go. So minus x plus x plus x in the stoichiometric ratio. 1.5 minus x, just add down, still lots, x and x. Go ahead and try to finish this problem. Pause the video. Alrighty. I presume you wrote the relevant Ka expression. Ka, the acidic constant, is H3O plus, the products, CH3COO minus, over the reactants, CH3COOH and water. And we always set water equal to 1, so this drops out of the equation. Then substitute in x and x for these 2 species. That gives us x squared on the top, and this is 1.5 minus x on the bottom. You have to look up the Ka value, then do some more math, and you should have calculated that the pH was 2.284, and the assumption you make that 1.5 minus x is approximately equal to 1.5 does turn out to be good. Again, our pH is acidic, 2.2, 2.3, and it has 3 significant figures, 1, 2, 3, 1, 2, 3. Remember that this first number after you take the log is not a significant figure. So, not surprisingly, a weak acid solution produces a pH that's in the acid range. All right, now add on the new stuff. Here's a new picture, and there are 4 lines on this picture, and I'd like you to try to figure out the identities of all 4 species in an aqueous solution of acetic acid. Use the hint that lines for conjugate acid and conjugate base species cross at the place where pH equals pKa for the acidic species. So that's a hint that should help you with this. Go ahead and pause the video and see what you can do. Hopefully with the hint, this wasn't too bad. You know the water species already. So H3O plus and OH minus are the ones that cross at a pH of 7, and H3O plus is high to the left and OH minus is high to the right. Those are straightforward. The only other species in solution, if you look back at your answer to the previous problem, were acetic acid and acetate anion. The acetic acid and acetate lines cross at the pKa for acetic acid, which is about 4.7. So if we come up to 4.7, we see two lines crossing there. Right at 4.7, you have the same amount of acetic acid as you do acetate in the solution. Any more acidic than that, and you have the protonated form as the stable, abundant form. So the acid form is always to the left, and the conjugate base form is always to the right of the crossing place at pH equals pKa. Here we have acetate in abundance at more basic pHs than 4.74, and acetic acid in most abundance at more acidic pHs relative to 4.74. Now let's talk about the recipe that we actually had. We looked at 1.5 molar acetic acid, and we calculated that it had a pH of 2.284. So our specific recipe would place us right here on this abundance diagram. And if you characterize the major species there, it would be CH3COOH, the acid form, acetic acid, and H3O plus. And the minor species would be the conjugate base, acetate anion, and OH minus. If you go to a pH of 5, you've got to read the diagram. OH minus is a minor species. CH3COOH, the acid, is a minor species. Coming straight up. The acetate anion, the conjugate base, is a major species there. And up further, the H3O plus is still a major species. If we go up to pH 11, now we have the H3O plus as a minor species, the CH3COOH as a minor species, there's H3O plus, and there's the acetic acid. Those are both minor there. And major species are the OH minus and the acetate anion. Moving right along, we'll go through outcome 26, pause the video, and do this problem. This is the outcome where you're either given a weakly acidic salt or a weakly basic salt, and there are actually 3 reactions you need to write. So pause the video and write out the answers to this outcome. Alrighty. I hope you remembered that the first thing you do is dissociate the salt. So there's this sodium acetate salt, dissociates into sodium plus and the acetate anion. Na plus is one of the alkali metal cations, so it doesn't have acidic or basic properties and will just float around as itself. But this is the acetate anion, which is the conjugate base of acetic acid, so it is a weak base. That weak base will react with water, and this time with a double arrow reaction, meaning that it's weak, it will form OH minus and the acetic acid back. So it gains a proton from water, leaving the OH minus, and it becomes the acid form. Label the conjugate acid-base pairs here. Up here we didn't have conjugate acid-base pairs, but we did have a single arrow because salts dissociate completely. And finally the water-water reaction. Because of this single arrow, this is an if table rather than an ice table. We have none of the salt left, but we have the 2 ions present, 6 sodiums and 6 acetates. However, of these 6 acetates that you start with, one of them is going to react in this next subsequent reaction, leaving only 5 of those, and 1 OH minus and 1 acetic acid molecule. And of course the water-water reaction occurs as well. So if we look at what's in solution, we don't have any of the salt. We have 6 sodium cations because they don't do anything after they are initially formed. But the acetate anion does go on to react, so the 6 that were formed, 1 of them goes away and forms acetic acid, leaving 5 acetates, still lots of water. The OH minus, we're forming 1 in this reaction and 1 in the reaction below, so we have 2 total OH minuses, and one acetic acid and one H3O+. So this would be a little bit more basic solution than it is acidic, more OH minus than H3O+, and quite a bit more acetate anion than acetic acid, and that'll be significant when you try to draw the abundance diagram, so pay attention to those. If you were asked to calculate the pH of this solution, you remember that it's kind of a pain in the butt process. You have to do an if table, figure out how much acetate you have, and then use that acetate in a Kb reaction, a base reaction, to form the OH minus and the acetic acid. This is an ice table, so 1 molar minus X, X, X. Here's your Kb expression this time instead of a Ka, because you're starting with the weak base and it's a Kb reaction. So you have different species in this. Again, the water drops out. Plug in the x's, x squared over 1 minus x. Go ahead and pause the video and do the calculation, make your assumption. And hopefully you got Kb. You had to calculate Kb by looking up Ka and then calculating Kb equals Kw over Ka. You may have initially thought that X was going to be pH, or give you the H3O+, but X is actually OH minus here, so the pOH is 4.63, and the actual pH is 9.37, which is good because it should be a base. This is a weakly basic salt, and the assumption turns out to be very good here. Here's the percent abundance versus pH diagram for this situation. Please pause the video and fill in the identities of all these lines. All right, I hope you're getting the hang of this. First, the H3O+ and OH- are easy to fill in. The acetic acid and acetate are always going to cross at the pH equals pKa place, and the acetic acid will always be the abundant species at low pH, and the acetate will always be the more abundant species at high pH. That leaves the only other species that's floating around in this solution besides water as the sodium cation, and it doesn't change with pH. It's high, it's 100% abundant at all pHs because it doesn't have any acid or base properties. It's just a neutral cation. The pH that we found for this solution was 9.37. It was a basic solution. So for the recipe 1 molar sodium acetate, we're right here. The major species are OH-, the acetate anion, and sodium cation at a pH of 9.37. And the minor species there are the H3O+ and the acid form of acetic acid. If we go down to a pH of 5, we see that the minor species are OH- and the acetic acid. Major species are H3O+, the acetate anion, and finally the sodium cation. So our major species are sodium cation, H3O+, and acetate, and our minor species are the acetic acid and the OH-. If we go all the way down to a pH of 2, right here I guess, we have OH- as a minor species, acetate anion as a minor species, and as major species, the acetic acid, the H3O+, and the sodium cation. And that is the end of that.